Okay, so this chapter, chapter 10, is going to kind of be the last chapter that we are going to discuss this semester. So in this chapter, we're going to start talking about the physical state of matter known as gases, right? So ideally, we would have also gotten to the next chapter, which was chapter 11, which dealt with solids and liquids. Unfortunately, we will not. So we will end our discussion of general chemistry by talking about gases, okay? Okay, so who cares? Why do we care about gases? What's interesting about them? So first off, we start with talking about gases when we start to move in to our various physical states of matter because they are considered to be the simplest. Gases tend to be simpler and more easily understood comparatively to liquids and solids. Okay, so number one, why gases, right? So who cares? What are we trying to learn about them? What do we want to know, etc. So number one reason why we actually study gases is because of all of the physical states of matter, gases are the simplest form of matter, the simplest state of matter, right? So gases are the simplest form of matter, okay? So understanding their behaviors and their various properties is going to help us in understanding lots of different things, especially with respect to solids and liquids, which tend to be a little bit more difficult to understand, okay? So number two, even though they are fairly simple and they're fairly accessible, they still are capable of lots of various things. So number one, for example, the properties and behaviors of gases allow airplanes to fly in the air, right? They also are at least responsible for a lot of the various weather phenomena that we see with respect to things like tornadoes and hurricanes and all of these various things, right? So they can hold jumbo jets up, they can also knock buildings down, right? So they may be simple and they may be kind of considered benign or harmless, but they are capable of a variety of different things like those two things, right? So with respect to understanding gases, what we're trying to do here is we're trying to understand their properties and the various laws that govern their behavior as well as their properties. So, what is the one basic property that helps us understand the behavior of gases? So, the answer to that is the concept of pressure. Right? So, pressure is defined as the force exerted by something per unit area. And you may question how a gas can exert a force, right? So this is going to lead us into one of the basic assumptions that we make with respect to gases is the fact that gas molecules are constantly moving, right? So if they're constantly moving, then they are going to be constantly colliding with the surfaces that contain them. And in that collision, it's that collision that exerts this force that generates the pressure that they do generate. So you may think, well, a gas molecule must be really, really, really tiny, and they are. They're very, very, very small. But there are a bajillion, gazillion gas molecules that are in the air around us that we breathe, right? So even though these collisions are tiny and generate very, very, very small forces, it's the combination of all of these collisions from all of these various gas molecules that exert this overall pressure that we see with respect to our gases, right? So one of the big properties that explain the behavior of gases is pressure, and again, pressure is the result of all of these little collisions of gas molecules with the surroundings around them. All right, so pressure is going to depend on a lot of different things. The pressure that a gas exerts is going to depend on a lot of the different parameters that the gas is actually experiencing, right? So, number one, the number of gas particles is going to have an effect on the overall pressure. So if you think of it, if there are more particles, so more particles, that leads to more collisions, and then more collisions is going to lead to a larger force and a larger pressure as well, right? So number of gas particles is going to be one of the big factors with respect to what affects the pressure of a gas sample. Number two is going to be the volume of the container. So if you think about a smaller volume, So a smaller volume is going to have the gas molecules with less area to move around in. That's going to result in more collisions. So more collisions, and again, an increase in pressure because of that. Larger the volume, the more movement they have, so the less collisions and the less pressure. And then the last little factor we're going to look at is speed, so the average speed of a gas particle. So if gas particles are moving faster, so if they have a larger overall speed, that means one of two things. Number one, we're going to get more collisions because they're going to collide more often. They're moving faster. Again, more collisions means more pressure. So pressure increases. Another thing that's going to result in moving faster is they're going to hit harder, right? So the faster you're moving, the harder the force you actually exert when you collide with someone. And so again, if you hit harder, then you're going to increase pressure as well. Okay, so lots of different factors that affect the overall pressure that is exerted by a gas sample. So number of molecules, volume of the container, as well as the speed of the molecules themselves. All right, so how do we actually go about measuring pressure? So the common unit and kind of how we got our understanding and initially measured pressure in the laboratory is something called the millimeter of mercury, right? So this is abbreviated mmHg. So anytime I say mmHg, just note that I am referring to a millimeter of mercury. So why the millimeter of mercury? That's kind of a good question overall. All right, so this whole idea behind a millimeter of mercury dates back to the invention of the original apparatus that was designed to measure pressure, which was called a mercury barometer. So mercury barometer, and this is still something that is in use today. All right, so what is the idea behind a mercury barometer? So a mercury barometer is designed as follows. Okay, so number one, mercury barometer consists of a glass tube. So we have a glass tube, and that glass tube is evacuated. Evacuated, meaning that there is a complete vacuum inside of it. Okay, so that's number one. Number two, we also have this large vat of mercury. So mercury is an element. In its elemental form, it is a liquid at room temperature. It's one of the only metals that are liquids at room temperature. And so in a mercury barometer, we have this nice large vat of liquid mercury. Okay. All right. So what happens with our evacuated tube in our vat of mercury? So the second little component of this is that we're going to take our evacuated tube and we're going to stick it into this little vat of liquid mercury. Okay. Now, the whole idea behind this is that the pressure that is exerted by the gas molecules in the atmosphere will push down on this vat of mercury, right? So they're exerting a force, they're exerting a pressure, and will essentially move the mercury in this tube up a certain distance, right? So the pressure exerted by the atmosphere pushes down, and the mercury moves up into the tube. And what we find is that the pressure of the atmosphere is capable of supporting a column of mercury about 760 millimeters in height. Okay? And so that's where we get this whole idea behind millimeters of mercury. We had originally measured all pressures via the mercury barometer, and the mercury barometer is where we get this idea of, the atmospheric pressure and how much a pressure or an atmosphere should actually support. Okay, so that's a mercury barometer. That's where we get our idea behind measuring pressure. You may ask yourself, well, why do we utilize mercury, right? So mercury, number one, is toxic. If you come into too much contact with it, it's very bad for you. It's also a very dense liquid, right? And so why do we use mercury? Well, if we use water instead, which is much less toxic, water is not as dense, right? And so if you do the exact same thing, have a vat of water and stick a nice little evacuated tube in it, then the pressure of the atmosphere would be able to support a column of water that was over 10 meters in height, right? So 10 meters is 30 feet, right? So you imagine this column with this tube of water that's 30 feet in the air. That's not super applicable for utilization in any type of laboratory setting, right? So comparatively, 760 millimeters of mercury, this ends up being about 29 inches of mercury if you convert, which is between about 2 to 3 feet in height. So this is much more practical for actual utilization in the laboratory. And the reason why it's so much smaller is, again, because mercury is so dense, whereas water is not very dense. Okay, so original unit of pressure was the millimeter of mercury. From there, though, we have lots of different ways to measure pressure. Okay, so from the mercury barometer, we know that the pressure of 1 atmosphere, or the gas particles that compose the atmosphere, support a column of mercury 760 millimeters, right? And so because of that, those are two of our various units that we use to measure pressure. So one of them is the millimeter of mercury, the other one is the atmosphere. And so 1 ATM, this is the abbreviation for it, is equal to 760 mmHg, okay? So another way that we can measure pressure is something called the torr. So the torr is named after the inventor of the mercury barometer, whose name was Torricelli. A torr is defined as a millimeter of mercury, right? So these guys are all equivalent. So 760 torr is equal to 760 mmHg is equal to 1 atmosphere. So again, these are all just various units by which we can measure pressure. So the SI unit is neither of these. The SI unit for pressure is something called the Pascal. This is a derived unit, right? So remember that pressure is defined as force per unit area. And so the SI unit for force is the Newton, and then the SI unit for area is just the meter squared. So the Pascal is a Newton per meter square. Importantly to note, the Pascal is very small, right? So it's not super great to utilize a Pascal because you'll be utilizing so many of them if you're considering the pressure of the atmosphere. Instead, what we frequently use is the kilopascal. So 1 ATM is equal to 101 kilopascals. And then a couple more, we have 1 atmosphere is also equal to 29 inches of mercury, because an inch, or 29 inches of mercury, is equal to 760 millimeters of mercury. That's just a unit conversion. And then finally, one other way that we measure pressure is the PSI. This stands for pounds per square inch. I don't need to actually spell out square inch here. No. So pounds per square inch. And again, this is an old British type of unit. We don't generally use PSIs in chemistry, but you will be much more familiar with them anytime you're filling up your bike or car tire. You generally measure pressure of tires in PSIs. Okay, so now that we have defined the various units of pressure, how we're actually going to measure pressure, we're going to start talking about something called the simple gas laws. All right, so for any sample of gas, there are 4 basic parameters or 4 basic properties that essentially define that sample of gas. Okay, so those 4 basic properties are the pressure of the gas, which we've been talking about, the volume of the container it's in, the temperature of the gas, and then the amount of it, and this is amount of gas in moles. Okay, so the idea behind the simple gas laws is that we're going to look at how pairs of these properties are related to one another when we hold the other 2 of the properties constant. So again, these are 4 basic properties. The simple gas laws look at how pairs of these react with respect to one another while we hold the 2 things constant. So the 3 gas laws, or the 3 simple gas laws that we look at, are Boyle's law, Charles' law, and Avogadro's law. Boyle's law is going to look at the relationship between volume and pressure when we look at a constant N and T. Charles' law is going to look at volume and temperature at constant amount and pressure. And then Avogadro's law is going to look at the relationship between volume and amount at constant temperature and pressure. And again, it's important to note that all of these laws were determined essentially experimentally by changing one of the variables and seeing how the other variable actually responded. So the first of the simple gas laws that we look at is something called Boyle's law. So Boyle's law is going to look at the relationship between volume and pressure, right? And it was studied by this dude named Robert Boyle back in the 1600s, which is a very long time ago, right? And so what he was looking at is the relationship between volume and pressure, and he was using something called a J-tube to essentially study that relationship. So in a J-tube, what you essentially have is a sample of gas that is trapped in the top of the tube. Again, this is stoppered here, and that gas is trapped, and there's pressure being exerted on it by a bed of mercury, right? And so what he would do is he would pour more mercury into this tube. That would increase the pressure overall, and what he would see is a decrease overall in volume, right? So the volume would get smaller. So he found from that there is an inverse relationship between volume and pressure, and mathematically, if we want to denote that, we usually show that as volume is proportional to 1 over P, right? So this is an inverse relationship. The larger the pressure, the smaller the volume, and vice versa. So we can utilize that proportionality, that volume is inversely proportional to pressure. Just as a note, mathematically, anytime we want to get rid of this guy, this proportionality sign, and replace it with an equal sign, we can do that. We just have to include a constant, right? So if we take this guy and we put the equal sign in, we just have to include a constant as well. So what we're going to get is the product of volume times pressure is equal to a constant. So what follows from that is that if you have a sample of gas at a certain volume and pressure and you change the volume, right, their product still has to remain this exact same constant. So we get overall this formulation of Boyle's law, right, where the volume of one state times the pressure of one state is equal to the volume at a different state times the pressure at a different state. And again, the big constant or overall constant behind this is that we have the same exact amount of gas, so number of moles of gas, as well as the gas is at the exact same temperature. All right, so this is Boyle's law. The second simple gas law that we look at is called Charles's law. So Charles's law looks at the relationship between volume and temperature. And again, the two other parameters that we were holding constant here is amount of gas as well as the pressure. So these guys are constant, and we're just going to vary volume and see what happens with respect to temperature, right? So what we find with respect to volume and temperature is that volume is directly proportional to temperature. So the higher the temperature, the larger the volume, and vice versa. We can also derive a nice little relationship or a nice little thing out of Charles's law, right? So let's say that we took a sample of gas at a specific volume, right? And again, had the exact same number of moles, exact same pressure, and we decreased that temperature of that sample of gas. So we started at really hot temperatures. This is temperature in Kelvin, and we decreased it, right, all the way back to 0. So this is 0 Kelvin. At 0 Kelvin, we would also essentially be at 0 volume, okay? So this relationship between volume and temperature says that at 0 Kelvin, we're at 0 volume, and that's essentially what defines the absolute temperature, right? So our absolute temperature scale is in kelvins and has a minimum value, a value that it cannot go past, and that is 0 Kelvin. The big idea behind that is that if it did go past it, right, if it did go past it, then we would be in negative values for volume, which is an impossibility, right? So when we can take these various relationships between volume and temperature, we can plot them, and we find that everything extrapolates back to this 0 Kelvin. Again, if we go past that to negative kelvins, we would be in negative volumes, which is a physical impossibility. So it tells us that absolute zero is the 0 Kelvin. Okay, so then we're going to utilize that. So again, we have this nice direct proportionality between volume and temperature. If I want to replace this proportionality sign with an equal sign, I can do that, but I have to include a constant. So now volume divided by temperature the quotient of these two is equal to a constant, and that's going to hold constant. It's going to be the same constant even if we change the volume and temperature, right? So this quotient of these two is always going to be constant as long as we are at the same amount and the same pressure, right? And so this formulation overall is called Charles's law. And as an important little note for you guys to remember is that Charles's law is based on the absolute temperature scale, right? That's where we got absolute zero, is this relationship between volume and temperature. So these temperatures have to be in Kelvin, right? So T in Charles's law, as well as T in any of the gas laws, always have to be converted to temperatures in Kelvin. You cannot use Celsius or Fahrenheit. Okay, so molecular view, let's try to understand why Charles's law is the case. So we talked about pressure being what essentially influences all of these gas laws. If we decrease the temperature, what we're going to do is decrease the kinetic energy of our molecules that are in our sample, right? They're going to move slower, number one, and because of moving slower, they're going to hit less frequently to the walls of the container, and they're not going to exert as much force, right? So overall, if pressure has to remain constant and we're decreasing the pressure by not having all of these collisions, then to get that back up, we need to decrease the volume. So that's why we see the volume decrease at low temperatures, whereas the volume will increase at high temperatures. That's why we get this direct proportionality between temperature and volume. Okay, and then finally, last simple gas law looks at the relationship between volume and the amount of gas, and this amount of gas is measured in moles. So intuitively, this one kind of makes sense, right? If you blow air into a balloon, what happens to the overall volume of the balloon, right? It expands. So this is, again, going to be another direct proportionality. The more moles of gas there are, the more collisions with the surface, the larger the overall volume. So again, we have a direct proportionality, and this is given by Avogadro's law. And so using the exact same stuff for the exact same mathematics that we did for both Boyle's and Charles's law, we can essentially derive an equation that relates the volume at a certain state and the amount of moles of gas at a certain state to the volume at a different state, number of moles of gas at a different state. And again, the two things that have to be constant for this relationship to work are the temperature and the pressure. Okay. So let's utilize an example here. So in this example, we have a sample of gas, right? So sample of gas, it has an initial volume of 13.9 liters and a pressure of 1.2 atmospheres. If we decrease the volume to 10.3 liters, the question is what happens to the pressure, or what is the new overall pressure? So this is looking at the relationship between volume and pressure. Oops, that's not right. This is looking at the relationship between volume and pressure, and Boyle's law tells us that relationship. It tells us that volume is inversely proportional to pressure. If we have a sample of gas and it's at one set of conditions, then the product of those conditions have to equal the exact same thing if we change one of those things. So Boyle's law is volume times pressure is equal to volume of the second state times pressure of the second state. What I'd like to do here is I like to define V1 and P1 and then V2 and P2. So we'll say that this is volume 1, this is pressure 1, and then the second state, this is volume 2, and we're solving for pressure 2. All right, so I'll go ahead and plug all of those in. So volume 1 is 13.9 liters. This is time pressure 1. So this is 1.22 atm. This is equal to volume 2, which is 10.3 liters. We compress it, and we'll be solving for pressure 2. So when we multiply these guys and divide, we end up getting x equal to 1.65. And when we do all this, the liters will cancel and we'll be left in units of atms, atmospheres. Okay, so again, the initial identification of this is that it is dealing with Boyle's law. We have the relationship between volume and pressure. And then it's just utilizing Boyle's law, knowing that it's V1 times P1 is equal to V2 times P2, and solving for whatever is unknown. Okay, so go ahead and try this one on your own. I'll go through the answer of it so you can pause this and then try it and then come back and see if you got the correct answer. This is looking at the relationship between volume and temperature. So just as a helpful hint, this is looking at Charles's law. So Charles's law, and most importantly, just remember that temperature has to be in a certain unit. And you will have to identify what unit that is. Okay, so hopefully you've tried that on your own. We're going to go ahead and identify what we know here. So Charles's law looks at volume and temperature, and we know that these guys are directly proportional to one another. The actual formulation is V1 over T1 is equal to V2 over T2. So we're going to go ahead and define some things. So V1, I'm going to let be this 48.3 milliliters. T1 is this guy, 22 degrees Celsius. Then we'll be solving for V2. That'll be our unknown. And T2 will be our 87 degrees Celsius, okay? So now before we can put this into Charles's law, we need to convert these guys. You don't necessarily have to convert the volume, but you will long term with respect to the ideal gas law. So let's go ahead and convert this volume to liters. All right, so if I want to convert the volume to liters, I just need to move the decimal 3 places to the left. So this is going to be V1 equal, that's not VI, V1 equal to 0.0483 liters. And then T1, we do have to convert this, remember, to Kelvin, right? This absolute relationship, or this relationship between volume and temperature is only applicable in temperatures of Kelvin. You will get a different answer if you put this in Celsius, and it will be incorrect. So to do that, we're going to take our temperature in Celsius and add 273. All right, and so when we do that, we get a temperature of 295 Kelvin. And then same thing here, we have to convert this guy to Kelvin, so we'll let this be unknown. T2 is going to be 87 plus 273, which gives us a 360 Kelvin. So now we are ready to plug in. So we've got this guy, we'll go down. We got 0.0483 liters divided by 295 Kelvin is equal to X. So it'll be our unknown over 360. So I'm going to cross multiply here. So I've got 295x is equal to the product of these guys. This is 17.4. And then x ends up being 0.0589. And this is in liters. And again, just to kind of get an idea of what the actual size of this is, if I want to convert to milliliters, I just need to move the decimal back 3 places to the right. So this is equal to 58.3 milliliters. Okay, so this is another little tricky type question. We're just trying to get you to understand the relationships between these simple gas laws. So we have a sample of gas, and in this problem we double the pressure at constant temperature, and then we take the same sample and we double the temperature at constant pressure, right? So the first thing we do, double the pressure at constant temperature, and then we double the temperature at constant pressure, and we want to know what the final volume of the gas is. So go ahead and think about this and then try it on your own and then come back for the correct answer. Okay, so for this one, we're looking at the volume. I think maybe I said this incorrectly when I read out the problem initially. We're looking at the volume of a sample of gas, right? And the first thing that we do is at constant temperature, constant amount, we double the pressure, right? So we're looking at volume. The first thing that we do is we double the pressure, right? And so if we double the pressure, the relationship between volume and pressure is inversely proportional. So we double the pressure, that means that we're going to half the volume, right? So volume will be 1/2 of its original amount. But then in the second step, when we have this half volume, what we're going to do is we're going to double the temperature at constant pressure. And so temperature and volume have a direct proportionality. And so if we double the temperature at constant pressure, we're going to double the volume. And so long term, what that's going to do is we're just going to be left with the exact same volume. Right? So my little schematic probably doesn't make much sense, but again, if we double the pressure, that's going to half the volume. If we then take that and double the temperature, because of the direct proportionality, it will double the volume. So we'll be back to the initial volume of the gas. Okay, so we have all of these simple gas laws at this point in time, right? And they all relate volume to one of the other parameters, right? So we have volume and pressure, we have volume and temperature, and volume and amount, right? So we can go ahead and combine all of these because we have this constant or this proportionality between volume and all of these things. So we can combine these to form volume is proportional to temperature times amount over pressure. And again, I'm going to go to black for now. And again, if we want to remove this proportionality sign and we want to replace it with an equal sign, we can do that as long as we include a constant. And that constant that we're going to include is what we're going to label as R. This is going to be called the ideal gas constant, right? And it's going to have a constant value. So if we do that, we have R times T times N over P. We can rearrange this and multiply both sides by P to get P times V is equal to nRT, right? And so what we derive from this is something called the ideal gas law. Okay, so pressure times volume is equal to amount times temperature times this constant value. Okay, so what is this constant value? So again, R is called the ideal gas constant. And unfortunately, R takes on a different numerical value depending on the units that we use, right? So for right now, the numerical value, the number for R that we're going to use is this 0.08206. But our units have to be atmospheres times liters divided by moles per Kelvin. So that means that all of our pressures have to be measured in atmospheres. All of our volumes have to be measured in liters. Our amount has to be measured in moles, and then our temperature has to be measured in Kelvin. So we will have to convert to get everything in these particular units when we utilize this value of R. Right? But the ideal gas law gives us this nice little handy tool that if we know 3 of these 4 things, then we can solve for the other given the fact that R is a constant. So let's go ahead and try one of those, right? So we have a sample of gas and we are given the volume of it. So it's the 8.5 liter tire. It contains 0.552 moles at a temperature of 305 Kelvin. And we want to know what is the tire pressure, both in ATM and PSI, of the gas in this tire. Right? So now we are given volume, we are given amount, and we are given temperature, and we're going to be solving for pressure using PV is equal to nRT. Okay? So again, our volume has to be in liters. It's already in liters, so that's great. Our amount has to be in moles. It already is. And our temperature is in Kelvin. So I have given myself a nice little easy problem where I don't have to convert anything. All I have to do now is just substitute. So I'm going to define this pressure as this unknown variable x. So x times volume, substitute that in, is equal to amount in 0.552 moles times R, which is 0.08206, and this is in liters times atmospheres over moles per Kelvin, and then times temperature. Why did that go back? Which is 305 Kelvin. So I'm going to go ahead and divide both sides by the 8.5 and multiply everything out. And I wish I had done that before. 0.552, oops, 0.552, 08206 times 305 divided by 8.5 gives me an x equal to 0.897, and we're solving for this in ATM. Actually, no, I just redid the calculations. So multiply everything out and divide by 8.5, we end up getting 1.62, and the moles will cancel here, the liters will cancel, the kelvins will cancel, the liters will cancel, and be left in units of ATM, which is good because that's a pressure. So this is 1.82 ATM. That's what they wanted. They also wanted this converted to PSI. So the conversion between 1 ATM and PSI is 14.7. So for every 1 ATM, there are 14.7 PSI. That's going to give me 23.9 pounds per square inch. Okay, so fairly straightforward, just plugging in the various values and solving for the unknown. So go ahead and give us a shot. We want you to determine the pressure, but we want it to be in millimeters of mercury, and we give you the volume, we give you the volume of this helium sample, we give you the temperature, and we give you the amount, right? Unfortunately, a lot of these units don't match up to what they need to be in to utilize the ideal gas law. So the first step in this would probably be conversion. So go ahead and try that and then come back for the answer. Okay, so we're going to go and start doing this one. Right, so we're looking at determining the pressure, given the fact that we know volume, temperature, and amount. So I'm going to go ahead and write our ideal gas law, not in highlighter. So PV equals nRT. And I'm going to go ahead and start writing stuff that we do know. So for the amount in, we don't have it in moles, right? We have 0.133 grams, and specifically that's of helium. So we can go ahead and convert this to moles, right? If we have a mass or something, we can convert it to moles. We just need to divide by the molar mass. So the molar mass of helium, if we look on the periodic table, is 4. So it's about 4.00 grams for every 1 mole. Right, and so when we divide by that, we get a 0.0333 moles of helium. Okay, so that's in. Then we also have volume. So volume right now is 648 milliliters, but again, this has to be in liters. So we'll go ahead and convert by dividing by 1,000, moving the decimal 3 places, which gives us 0.648 liters. And then temperature right now is in Celsius. It's 32 degrees Celsius. So to convert that to Kelvin, we just need to add 273. That gives us a 305 Kelvin. Okay, so now I'm going to go ahead and isolate P by dividing both sides by V. So pressure is equal to nRT over V. And then I'm going to go ahead and start substituting things in. So I've got N. So I'm going to go ahead and start substituting in. My N is, stop it, 0.0333 moles. My R is the gas constant, so 0.08206. My temperature is in Kelvin, it's 305 Kelvin. And then my volume in liters is 0.648 liters. All right, so this is my pressure. When I solve, I'll end up in units of atmospheres, and that ends up being 1.29 ATM. But then this last little step, they want us to convert that to millimeters of mercury. And so the conversion between ATM and mmHg is 1 ATM is equal to 760 millimeters of mercury. So we'll go ahead, for every 1 ATM, you get 760 of these guys. So we multiply that out, we end up with 977 millimeters of mercury. Okay, so that is the ideal gas law, okay? And we're going to be utilizing that with respect to the remainder of the chapter, okay? All right, so a couple of things we're going to define now. The first one is something called standard conditions. So unfortunately, the volume of a gas depends on a lot of different variables, right? So the volume depends on the pressure, it depends on the temperature, on the amount, right? So what we have kind of done so that we can compare measurements from different experiments with respect to one another is we have defined a standard set of conditions. This is called standard temperature and pressure. So it essentially kind of removes the variability with respect to temperature and pressure on the volume of a gas. And we abbreviate standard temperature and pressure STP. Particularly, the standard pressure is defined as 1 atm, and the standard temperature is 0 degrees Celsius or 273 Kelvin. All right, so with standard temperature and pressure, with STP, we can also define something called the molar volume, right? So this is going to be defined as the volume of 1 mole of a gas at STP. Okay, so if we go back to the ideal gas law, we have PV equals nRT. If we're looking at the volume of 1 mole of gas at STP, then we're going to solve for volume. So this is nRT over P. And again, we've defined all of these unknown parameters when we're looking for molar volume at STP, right? So molar volume, N is 1 mole. Temperature is 273 and pressure is 1 atmosphere, right? So we can go ahead and plug all of these in. So 1 mole times our gas constant, 0.08206, times our temperature, which is 273 Kelvin at STP, divided by our pressure, which is 1 atm. What we find is this molar volume is 22.4 liters, right? And so any type of gas, 1 mole of it at STP will occupy a volume of 22.4 liters. This is also going to convert a nice little conversion factor where we will know at STP that 1 mole of a gas is equal directly to 22.4 liters. We'll come back to this in a second. Okay, so now that we have this molar volume, we can kind of apply that. It's going to be respective or irrespective of the gas, right? So if you have a mole of xenon, right, it's going to occupy the exact same volume, this 22.4 liters, at STP as a mole of a much smaller gas like helium, okay? So regardless of the molar mass, regardless of how big you want to imagine these molecules are, they're going to occupy the exact same volume. At STP, this is 22.4 liters. Now, the amount of mass that is going to be required to get to that 1 mole is going to be different with respect to each of these, so keep that in mind. Okay, so trying to apply that, I know it probably doesn't make much sense. We have 3 different gases. We have a gram of hydrogen, a gram of oxygen, and a gram of argon. I want to know which of these will have the greatest volume at STP. So go ahead and think about this and then come back for the answer. Okay, so again, with respect to this molar volume, we know that for every 1 mole of a gas at STP, it'll occupy 22.4 liters. So the more moles, the more volume is going to be occupied, right? And so right now we have all of these samples in grams. And so what you need to do to answer this problem is figure out which one of these gives you the most moles of gas, right? So for example, for hydrogen, diatomic hydrogen has a molecular weight of 2, approximately, like 2.018 grams per mole. So if you have 1 gram of it, right, and you converted that to moles, that would be, let's imagine it's just 2, we'll round it up, so 2 grams for every 1 mole. That would be about a half of a mole, right? We can just kind of estimate it. On the other hand, diatomic oxygen by itself is 16 grams per mole. 2 of them is going to be 32 grams per mole, right? And so if we have 1 gram of O2 and we divide by 32 grams for every 1 mole, we get about 1/32 of a mole, right? Which is going to be less than this guy. Now, argon, on the other hand, we've got 1 gram of argon. Argon has a molar mass, if we look on the periodic table, of about 40. So 40 grams per mole. So then again, if we have 1 gram of argon, if we convert that to moles, we'd get about 1/40 of a mole, which is less than this guy, which is less than this guy. So the one that gives us the most moles, and therefore the larger volume, is going to be the 1 gram of hydrogen. Okay, so a couple things that we can do with this molar volume now. So the first thing we're going to talk about is density. So for the density of a gas, this is just going to be, density period is always just the ratio of the mass of the thing divided by the volume of the thing. With respect to gases, we generally give this in grams per liter, but with respect to volumes or with liquids, we tend to measure this in grams per milliliter. So just note that with respect to gases, this is always usually measured in grams per liter, right? So how could we calculate the density of a gas? So remember that density is just mass divided by volume. We now know that the volume of 1 mole of a gas at STP is 22.4 liters. We also know that the mass of 1 mole of a compound is just going to be the molar mass and the molecular weight, right? So our molar masses are always measured in grams per mole. If we divide that by the molar volume, which is moles or liters per mole, 22.4 liters per mole, so this is in liters per mole, then overall our moles will cancel and we'd be left with units of grams per liter, right? So if we want to calculate the density of a gas and we are at STP, then all we need to do is take the molar mass of that gas and divide it by the molar volume, and we will find the density. So for example, if we want the density of helium, the molar mass of helium, we look up on the periodic table, this is 4 grams per mole. The molar volume for any gas is always 22.4 liters per mole, and so we get a density for helium of 0.179 grams per liter. Do the same exact thing for something like nitrogen. So nitrogen is diatomic. It has a molar mass of 2 times the atomic mass of nitrogen, which is 28 grams per mole. Same thing divided by the molar volume. That gives us a density of 1.25 grams per liter. All right, so notice that as we increased the molar mass, right, so molar mass increases here, what happens overall to the density, right? We see also an increase with respect to density. That is because density is directly proportional to molar mass, right? So the larger the molar mass, the larger the density. Molar volume. Okay, so the larger the molar mass of the gas, the larger or the more dense it is. Okay, other things that can happen, right? So that was particular for STP, taking the molar volume, taking the molar mass, calculating the density from that. You had to be at STP. What if we want to calculate the density, but we are not at standard temperature and pressure? So we can do that. We're going to utilize, again, the ideal gas law. And in utilizing the ideal gas law, we are going to solve for, or we're going to isolate N over V, right? So to do that, I'm going to divide both sides by R, and I'm going to divide by volume, and we're going to be left with this guy, right? So this is just the ideal gas law rearranged. This thing right now is in terms of moles per volume, moles per liter. This is what is called the molar volume, right? Or molar density. Yeah, molar volume, that's fine, right? So then to turn this in to the density in terms of grams per liter, all we need to do is multiply by the molar mass of the gas, right? So molar mass of the gas is in grams per mole. If we multiply this guy by grams per mole, the moles will cancel and we'll be left in terms of grams per liter. If we do it to this side, though, we also have to do it to the opposite side to make sure that we match up mathematically, right? So molar density times molar mass gives us the density in grams per mole. That's going to be equal to the pressure times the molar mass divided by R times T. Okay, so let's go ahead and use that. We're going to calculate the density of xenon gas at a pressure at 742 millimeters of mercury and a temperature of 42 degrees Celsius. So go ahead and try that and then pause it, come back for the answer. Okay, so we're going to calculate the density of this xenon gas sample. Again, we've moved away from STP, from standard temperature and pressure. So now we're going to utilize that equation that we just derived, where density is equal to the pressure times the molar mass, which we give this weird M. Just note that this is molar mass divided by R times T. That's a really ugly molar mass. So hold on just 1 second on this. Okay, well, that just messes everything up. So we have pressure times, I'm just going to write M, right, divided by R times T. Okay, so to calculate this, we need all of these various variables. We already know what R is. Pressure we are given. The pressure we are given is 742 millimeters of mercury. The problem is, though, that we, again, if we're going to use this value of R that we're used to, we need to convert this to atmospheres. So the conversion factor between mmHg and atmospheres is 760 mmHg, or millimeters of mercury, is equal to 1 atm. Right, so when I divide this by this, I end up getting a pressure of 0.953 atm. So that's pressure. All right, then we have temperature. So the temperature they give us is 45 degrees Celsius. Again, this has to be converted to Kelvin. So to do that, I'm going to add 273. And that's going to give me a temperature of 318 Kelvin. And then the last little thing is the molar mass of the gas. This is xenon. Xenon is monoatomic. It's a noble gas. So we'll just look up the molar mass from the atomic mass in the periodic table. This gives us a 131.29 grams per mole. So now we are ready to plug everything in. So we've got density is equal to pressure, so 0.953 atm, times molar mass, which is 131.29 grams per mole. This is going to be divided by R, which is 0.08206. This is liters times atmospheres times or moles times Kelvin. And then temperature, which is 318 Kelvin. Okay, so when we multiply and divide, we end up with a density here of 4.79 grams per liter. Again, the atmospheres cancel. The moles cancel, the kelvins cancel, and we are left with grams per liter, which is the density that we measure, or how we measure the density of gases. Okay, so another little helpful application of the ideal gas law is utilizing it to determine the molar mass of some sort of unknown substance, right? So let's say that you had some sort of unknown liquid, right? So let's say just like this pool of unknown liquid. It was same composition, so it was a pure substance here. Let's say that you did know the mass of it, but you didn't know what the overall molar mass of it was, right? So one way that you could determine what the molar mass of this substance is you could heat it, right? So by heating it, it would turn all of them into gases, and you could essentially measure the number of moles of the gas that was produced via the pressure, the volume, and the temperature using the ideal gas law, right? So you could trap this, let's say, measure the overall pressure, the volume, and the temperature upon heating this, and then you could utilize that data to calculate the molar mass, right? Because the molar mass of something is just the mass of it divided by the number of moles. So let's say that we do that, right? Let's say that we have a sample and we know that the mass of the sample is 0.311 grams, right? So we heat it, it turns into a gas, and from the resultant gas, we measure the volume of it, we measure the temperature, and we measure the pressure, right? So let's utilize that data to find the molar mass of this unknown. So what the pressure, volume, and temperature is going to tell us is the number of moles that were produced upon heating this unknown substance. To figure out the number of moles, we have to utilize the ideal gas law. So PV is equal to nRT. Okay, so I'm going to rearrange. N is equal to PV over RT. And I'm going to solve for the number of moles. Before I can do that, I have to convert a few things. So first off, I have to convert the pressure. Pressure right now is in millimeters of mercury. So I need to convert that first to atmospheres. Again, I'm going to do that by dividing by my conversion factor. There are 760 mmHg for every 1 atm. So when I convert this, I think I get a pressure of 1.17 atm. I also have to convert the temperature, unfortunately. So temperature right now is in Celsius. So I need to add to this 273 to convert to Kelvin. When I do that, I get a temperature of 328 Kelvin. Okay, so let me make sure I got everything right. Yes, I did. Okay, so now we can go ahead and substitute. I'm going to zoom back in. So N is equal to pressure, which is 1.17 atm, times volume. Volume here was 0.225 liters, divided by R. R, again, is our just ideal gas constant. And then the temperature is 328 Kelvin. All right, so we divide, multiply, do some stuff with respect to math, and we get the number of moles equal to 0.00978. Okay, so that's step number one. This is determine the number of moles. Step number two, you're going to utilize that to determine the overall molar mass of the gas. Okay, so we had a sample that initially had a mass of 0.311 grams, right? We heated that and it produced this many moles. So now to figure out the molar mass, we're just going to take the mass of the sample. Man, I don't know why this is so bad today. So 0.311 grams and divided by the number of moles it produced, 0.00978 moles. And we'll end up with a value of 31.8 grams per mole, which is the molar mass of this unknown gas. Fairly similar to 32, which would be oxygen. So you could maybe predict what type of gas it was, perhaps. Okay, so again, go ahead and try this. Okay, so we have another sample of gas. It's got a mass of 827 milligrams. We give you the volume, we give you the temperature, and we give you the pressure, and we want you to find the molar mass. So go ahead and give this a shot, and then come back for the answer. Okay, so same type of problem. We give you the mass of an unknown sample of gas, and we want you to calculate its molar mass. So to do that, you first have to calculate the number of moles there are. Let me change some things here. Right, and so we're going to utilize the ideal gas law to do that. So we can go ahead and write N is equal to PV over RT. That's just rearranging PV equals nRT to solve for N. We're then going to take our pressure. That's our first one. So pressure right now is in millimeters of mercury, which is bad. We can't plug it in like that, so we have to convert to atm. So to do that, we're going to divide by 760. When we do that, we get a pressure in atmospheres of 1.28. So same thing for temperature. Right now it's in Celsius. So we're going to add to it 273, and we get a temperature of 361. So we can go ahead and plug this guy in. So we've got N is equal to P, which is our 1.28 atm, times V. V was in liters already, so we have 0.270 divided by R, 0.08206, times temperature in Kelvin, which is 361 Kelvin. So N is 0.0117. So now for the molar mass, we'll just take the mass that they gave us. The only problem with this is that it's in milligrams. We need to convert to grams. So to do that, I'm going to move the decimal 3 places to the left, divide by 1,000. So this is 0.827 grams. So, I told us to do this. So this is mass 0.827 grams divided by moles, which is 0.0117. That gives us overall molar mass of 70.7, I think, grams per mole. Okay, so nice, simple stuff. Okay, so one little application, one more thing that we have to talk about before we move into kinetic molecular theory is the concept of mixtures of gases, right? So we're going to deal with things called partial pressures, mole fractions, etc., right? So what we have been looking at thus far is we have been assuming that we have a pure gas sample. So we've been dealing with pure xenon, pure whatever we're looking at, right? But in reality, in actuality, most gases are mixtures, right? So for example, the air that we breathe is a mixture of a variety of different gases. It is, in percent by volume, 78% nitrogen, it's 21% oxygen, it's got some argon in there, and it's got a bunch of other stuff that kind of makes up the remainder of the percent. And so the question is, well, if we're dealing with these mixtures quite a bit, can we treat them as we would an ideal gas? And the answer to that question, can we treat a mixture as if it was one gas and still utilize all of our little gas laws with it, is yes, right? So for the most part, most mixtures can be treated as one pure identical gas, right? This comes about in the fact that when we're dealing with gases, we're concerned not necessarily about the identity of the gas, but just about how many molecules there are. And the number of molecules aren't going to change even if it's a mixture, right? So for the most part, yes, we can treat mixtures as just one pure substance. So now, what else can we define if we're dealing with a mixture, right? So if we imagine that you do have a mixture, you have all these little gas molecules, you've got nitrogen, you've got oxygen, etc., and they're all moving around, and essentially what they're doing is they're all contributing their own little amount to the overall pressure of the gas, right? So we can define something called partial pressure, which is the pressure that is exerted by one of the single gases in a mixture. And we can calculate the partial pressure of a gas in the mixture via just our normal ideal gas law, right? So if we said that this was a mixture that had nitrogen and oxygen, and I wanted to calculate the partial pressure of oxygen, just the component of the pressure that oxygen is contributing to this overall mixture, all I would have to do is multiply the number of moles of oxygen times RT over V, right? So the partial pressure is related to how much actual molecules of that substance are in there, right? And so then, again, if we had like a mixture of nitrogen and oxygen, if I wanted the total pressure of the mixture, all I would have to do is sum up the two partial pressures, the partial pressure of nitrogen, the partial pressure of oxygen, and that would give me the total pressure. Okay, so this thing, just the formulation that the total pressure is just the sum of all of the partial pressures is something called Dalton's law of partial pressures. Okay, so all of the individual components, all of the individual partial pressures sum up to the total pressure of the mixture. Okay, so given Dalton's law of partial pressure, we can do a couple other things with these equations, right? So we have restated here Dalton's law of partial pressure. So for each of these partial pressures, we can go ahead and substitute in the ideal gas law for how we calculated it. So the partial pressure of A is calculated from the number of moles of A times RT over V. Same thing for partial pressure of V. And then we can factor out this RT over V. This is the same for everyone, right? And so when we do that, we end up with the sum of all of the moles of gas. So this is the number of moles total is equal to the total pressure times RT over V is equal to the total pressure of the mixture, which makes sense. This is something that we have been assuming. Okay, so now if we take, let's say, the partial pressure of A, right, and we divide it by the total pressure, and we go ahead and substitute in our little ideal gas laws for both of these, what we will find is that this guy cancels, and we are left with this number of moles of A over total numbers of moles, right? We are going to define this thing as a new overall term. This is going to be called the mole fraction, right? And so essentially what it is just the number of moles of whatever component we're looking at divided by the total number of moles, right? So the fraction that A makes up of the total, okay? So if we go ahead and substitute this guy in to our equation up here, right, for the fact that this now is defined as the mole fraction, we're going to be left with the partial pressure of A divided by the total pressure is equal to the mole fraction of A. If we multiply both sides by pressure total, we're going to be left with this little equation, which tells us that we can calculate the partial pressure of A if we know the mole fraction of A and the total pressure of the overall mixture. Okay, so again, this is dealing with a mixture. And just for the homework, as a note, mole fraction is defined here. So mole fraction of whatever component is just the number of moles of that component divided by the total number of moles of the mixture. Okay, so what's helpful about these mole fractions is that the percent by volume in a mixture can be directly converted to the mole fraction of whatever component we're looking at in that mixture. So for example, on that first slide, I had showed you that air, dry air, has 78% nitrogen, and that's by volume, okay? This can be directly converted to a fraction form. So the fraction form of this is 0.78, and that is the mole fraction of nitrogen in dry air, right? So we can utilize these percent by volumes in their direct conversion to mole fractions, right? So let's say that I wanted to calculate the partial pressure of nitrogen in dry air. We know that the total pressure of air is 1 atmosphere, because that's how we've defined the atmosphere. It's 1 atmosphere pressure. We also know that nitrogen is 78% of the overall volume of dry air. So we can convert that directly to mole fraction. With that, we can plug it into our partial pressure of nitrogen is equal to mole fraction of nitrogen times total pressure to calculate the partial pressure of nitrogen in the atmosphere. We can do the same thing for oxygen, right? So we'll find the same thing for oxygen, same thing for nitrogen. And again, using Dalton's law of partial pressures, the total pressure is just going to be the sum of all the partial pressures, which gives us our overall 1 atmosphere of pressure. Okay, so let's go ahead and try one of these with respect to partial pressures and Dalton's law of partial pressure. All right, so in this problem, we have a mixture of gases, right? So this mixture of gases contains both helium and oxygen, and the components of the helium is 24.2 grams, and the amount of oxygen is 4.32 grams. So in this problem, they want you to calculate the mole fraction and the partial pressure of each of the 2 components of the mixture, and then the total pressure of the mixture. Okay, so again, we have this mixture that has both helium and oxygen. And more specifically, we have 24.2 grams of helium, and we have 4.32 grams of oxygen. Okay, so 2 different things they want us to determine. They want us to determine both the mole fraction, which gets this little Greek letter chi. So mole fraction of both helium as well as mole fraction of oxygen. And then they also want us to determine the partial pressures of helium. That's not helium, that's hydrogen. Partial pressures of helium, partial pressures of oxygen, and then total pressure of the mixture. Okay, so lots of little things that we have to figure out. Okay, so first off, mole fraction. We'll start there. So with respect to the mole fraction, depending on what we're looking at, let's say that we start with helium, the mole fraction, why is it doing this? Okay, so the mole fraction with respect to helium is just going to be the number of moles of helium divided by the total moles of the mixture, okay? So with respect to helium, right now we don't have it in moles, we have it in grams. So our first step here is going to be to convert our grams of helium to moles of helium, and we're going to do that by dividing by the molar mass of helium. So all we have to do for that is look it up on the periodic table. Helium has an atomic weight, a molar mass of 4.00 grams for every 1 mole. So when we divide by that, we get a number, and it's fairly large, and that ends up being 6.05 moles of helium. Okay, and then for calculating the overall mole fraction, we need total moles. We also need to go ahead and convert the moles of oxygen here. So we have oxygen, we have 4.32 grams of oxygen, and so this is O2. To convert to moles, we're going to divide by the molar mass of oxygen. So this is 32 grams for every 1 mole. When we do that, we end up getting a 0.135 moles of oxygen. So moles of helium, moles of oxygen. So now total moles in total is just going to be the sum of those two. So we've got the 6.05 plus the 0.135, which gives us a number of 6.185 moles for total moles. And now all we have to do is plug in these values to calculate each mole fraction. So mole fraction for helium is 6.05 moles divided by total moles, 6.185, which gives us a mole fraction equal to 0.978. And again, it's a fraction, so there are no units here. I should make sure and note that those cancel. Same thing for oxygen, except now we've got moles of oxygen, which are 0.135, divided by total moles, 6.185, which gives us a fraction of a 0.022. Okay, so this is our mole fraction for helium, our mole fraction for oxygen. Okay, so as a note right here, because there's only 2 components in this mixture, you could have just taken what you got for helium and subtracted it from 1, because again, they all have to come up to the total fraction, which is 1. But again, for oxygen, you can go ahead and just calculate it this way as well. Okay, so then they want us to calculate both partial pressures and total pressure. So the route that I'm going to go about in doing this is I'm going to calculate total pressure first, and then I'm going to calculate the partial pressures from that. So total pressure, so P total, is equal to the total number of moles in this mixture times RT over V. And again, this is just coming from PV equals nRT, rearranging to solve for total pressure, okay? So we know total moles, that's going to be the 6.185. R is the gas constant, 0.08206. T is temperature, this is 298. And then we're going to divide by the volume, which was given to us. This was 12.5 liters. So total pressure here ends up being 12.1 atm. And so now, with total pressure, we can utilize that to calculate partial pressures. So partial pressures of anything in a mixture is just the mole fraction times the total pressure. Now we know both mole fraction and total pressure, so we can calculate partial pressures for both of helium and the oxygen. So for helium, this is 0.978. times total pressure, which was 12.1 atm. This is 11.8, that's an 8, 11.8 atm, and then that's an m. Good day, good day. Okay, and then for oxygen, we can do the same thing, except using its mole fraction, so 0.022 times 12.1, and we're left with, for this guy, a 0.266 atm. Okay, so we've got a lot of different answers here. We've got our partial pressures, we've got our total pressure, and we also have our two mole fractions over here. So as a note, with respect to Dalton's law says that total pressure is just the sum of the two partial pressures. So as a nice check, you can go ahead and sum these guys back up, and you should get 12.1 overall plus 0.266. We add these together, we do get the total pressure that we have calculated. Okay, so that is that. So go ahead and try this question. It's utilizing the same types of concepts, except it's kind of asking it in a different manner. So here they give you the mole fraction of oxygen in a heliox mixture, and they want you to calculate total pressure if the partial pressure of oxygen is 0.21. So go ahead and try that and then come back for the answer. Okay, so this is a little bit easier. They give us quite a bit of information on this. So this is going to rely on the fact that the total pressure, the partial pressure of a component of a mixture, so we'll say this is partial pressure of oxygen, is just equal to the mole fraction of oxygen times the total pressure. So they give us the partial pressure of oxygen, total, great, total, oh man, total, let's go back to red, total. So they give us the partial pressure of oxygen, so that's great. They give us the mole fraction of oxygen. So now we just have to substitute those guys in and solve for the total pressure here. So partial pressure of oxygen is here. We've got a 0.21 atm. This is equal to mole fraction, so 0.050 fraction, so there's no units here, times total pressure. So when we solve for total pressure, we end up getting a total pressure of 4.2 atm. So hopefully you guys got the same exact thing as well. Okay, so next we're going to be going back to a topic that we kind of covered pretty early in the semester, right? So as a reminder, we have been dealing with chemistry, right? And chemistry involves reactants and them going to make products, okay? All right, so if you guys recall, back in like chapter 3, we talked about stoichiometry, right? And in stoichiometry, that was going to give us the overall ratios for our various reactants and how many products they made, right? And that came from balancing the chemical equation. And so what that was going to allow us to do is, given a certain amount of reactants, we could figure out how many products we were going to form or how many other reactants we needed to use, and that's essentially what the purpose of stoichiometry was, right? So before we could do that, right, before we could go in and utilize these numbers that were in front of our various reactants and products, we had to first convert into moles, right? So before we could go into stoichiometry land, we had to be in moles. And in chapter 3, the way we usually did that is we were usually given grams, so grams of starting material, and to convert to moles, we divided by the molar mass, right? So one way that we utilized to get into moles was molar mass. Then in chapter 4, we talked about a different sort of reaction, right, where we had solutions and these were aqueous solutions, and we were reacting them together. And in that situation, to get into moles, to utilize the stoichiometry, we needed the concentration as well as the volume, right? So this was the molarity as well as the volume, make that a little bit better, as well as the volume. That would tell us the overall moles. Once we had the moles, we could move through this, okay? Now we're going to utilize the same exact ideas, except now we're dealing with gases, right? And with respect to gases, if we have reactions between different gases, we can also calculate the number of moles, except now we're going to be using the ideal gas law, right? So PV equals nRT. So now if we do have reactions between individual gases, we need to know the pressure, we need to know the volume, and we need to know the temperature of the gas, and then we'll utilize PV equals nRT to get into moles, and then we'll utilize the stoichiometry thereon. Okay, so again, very, very, very similar to what we've already done, except now we're going to be utilizing PV equals nRT to get into moles. Once we're in moles, we'll utilize the stoichiometry, and then depending on what we want to do, we can either utilize PV equals nRT again to get out in terms of volume of a gas, or sometimes they'll just ask for mass again, so it depends usually on how we come out of this. So one other thing to note, right, so to get from pressure, volume, temperature of a gas into moles, we will use PV equals nRT and solve for N. But if we're at STP, remember we've already solved for the molar volume at STP. So at STP, 1 mole of a gas equals 22.4 liters, right? And so we can also utilize this as a conversion if we are doing a reaction at STP between moles of a gas and volume of the gas, right? And I'll show you how to utilize that in the next slide. All right, so let's say that we have a reaction, right? And the reaction is between hydrogen and oxygen, and it's going to form water, right? And in this problem, we want to know how many grams, so how many grams of water form when we react 1.25 liters of hydrogen at STP, and we're reacting it with excess oxygen. So the fact that it says completely reacts with oxygen tells us that this is in excess, okay? So that this guy, hydrogen, is going to be our limiting reagent. Okay, so how are we going to utilize all this data to figure out how much product we produce, how much water we produce in grams? So first off, again, we have our balanced chemical equation. And before we can utilize these numbers in the balanced chemical equation, we have to first convert our starting materials to moles, okay? Again, though, we're dealing with a gas, and specifically that gas is at STP, and we are given a volume of it, right? So we can use PV equals nRT if we wanted to, but again, we have this conversion already that 1 mole of a gas at STP is equal to 22.4 liters. So I'm going to utilize that conversion to figure out how many moles I have of hydrogen, okay? All right, so again, we have 1.24 liters of hydrogen, and I know because we're at STP that for every 22.4 liters, I have 1 mole of hydrogen. So essentially we're looking at what fraction of this molar volume do we have at STP. So when we take our 1.24 liters and divide by 24, 1.24 liters divided by 22.4, that's going to give us liters canceling and 0.0554 moles of H2, okay? Equivalently, we could have used PV equals nRT. So if we rearrange, we have N is equal to pressure times volume over R times temperature. STP is standard temperature and pressure. This is a temperature equal to 273 Kelvin and a pressure equal to 1 atm. All right, so I can plug those guys in. 1 atm, volume is 1.24 liters over 0.08206, which is R, and then 273. When I solve for this, I end up with 0.0554 moles of hydrogen, right? So these guys are going to be equivalent, and it does not depend on how you actually go about solving this. I just chose the molar volume thing because to me it seemed a little bit easier. Okay. All right, so now we're in moles of hydrogen. So we've got our 0.554 moles of hydrogen. Now we want to convert this to moles of product, moles of water, and we're going to utilize the numbers that are in front, right? So they tell us that for every 2 moles of hydrogen, how many waters do I make? I make 2 moles of water, okay? So that's going to convert into moles of water. So when I take this number, I divide by 2, multiply by 2, it's the exact same number. So we end up with 0.0554, and this is moles of water now, because these moles of hydrogen have canceled. And now in the last little bit, they want us to know, or they want us to find out how many grams of water is formed, right? So now we're in moles of water. To convert back to grams, we need to multiply by the molar mass. So molar mass of water is just the sum of all the atomic masses of all of the elements that are present. So we have 2 times hydrogen, which has an atomic mass of 1.008, plus 1 times water, which is 16. This ends up being 18.018, and that's in grams per mole. So now there are 18.018 grams for every 1 mole of water. H2O. So we multiply these guys together times 18.018. That gives me a 0.997 grams of water produced. Okay. Okay, so again, now we just have a new way to get back, or to get into moles, so that we can utilize the balanced chemical equation to be able to convert between our various different things. Okay, so go ahead and try this one and then come back for the answer. So in this problem, unfortunately, we're not at STP. So we have some sort of solid. This is silver oxide. It's decomposing into silver as well as oxygen gas. And what has happened is we had a certain amount of this guy. So this is some unknown. This was in grams, though. It is completely decomposed, right? So completely reacted. And at the end of the reaction, we collected the oxygen, right? And when we did that, we collected 4.58 liters at a pressure of 745 millimeters of mercury and a temperature of 308 Kelvin. So they want us to utilize that data to figure out how much of this silver oxide in grams was initially there that decomposed. So go ahead and try this and then come back for the answer. Okay, so again, we can't use the STP conversion now. So to solve this problem, we're going to have to use PV equals nRT. So PV equals nRT. I'm going to solve for n. N is equal to PV over RT. And what I'm going to figure out right now is how much in moles was there of oxygen that formed, right? So how much oxygen formed in moles. So I've got my pressure. My pressure, unfortunately, is in millimeters of mercury. So I'm going to convert that first. So pressure is equal to 745 mmHg. To convert this guy, I'm just going to, why is it doing that? To convert this, I'm just going to divide by the conversion. So for every 760 mmHg, there's 1 ATM. It's going to give me 0.980 ATMs for the pressure. And then everything else, liters and temperature, they're all in the correct units, so we can go ahead and plug this in. We've got pressure, which is 0.98, times volume, which is 4.58 liters, all over R, which is 0.08206, times temperature, which is 308 Kelvin. So when we solve for moles here, we end up with 0.176 moles of oxygen, okay? So now, I should have written that in a better way. me see if I can use this nice little, nope, not possible. So undo that. Okay, so we're going to convert this guy. I'm going to rewrite it. So we're going to take this guy. We've got 0.176 moles of oxygen. Now, that's how many moles we produce, right? The question is, how much silver oxide decomposed to produce this many moles? So now we're going to utilize, now that we're in moles, we're going to utilize the stoichiometry of the reaction. So for every one of these that was made, we used 2 moles of these silver oxides, right? So for every 1 mole of oxygen, we use 2 moles of Ag2O. So I'm going to multiply by 2, the 0.176. 0.176 multiplied by 2 gives us 0.352 moles of Ag2O. And then finally, if we want to convert this to grams, we're going to have to multiply by the molar mass. So the molar mass of silver oxide is, there's 2 silvers. So 2 times silver is 2 times 107.9. And then we're going to add to that our 1 oxygen, which is 16. So let me write this a little bit better, grams per mole. So when we multiply 2 by 107, we add 16 to it. We end up with a molar mass of 231.8 grams per mole. So we'll take this guy, our 0.352 moles, and we will multiply by the molar mass to convert to grams. So for every 1 mole of Ag2O, we get 231.8 grams. So this is times 231.8 gives us 81. I wonder how I got that different. 231.8. This was, 0.176 times 2. Yep, okay, times 231.8 gives me 81.6 grams of Ag2O. Okay. So again, hopefully that is a nice little refresher about stoichiometry since you're about to take your final. This is just another way in which we can utilize this reaction stoichiometry if we're having reactions that involve gases, right? So for the gas, we'll need to know the pressure and the volume and the temperature, but then we can convert to moles via our ideal gas equation. Okay, so same thing-ish. This is a nice little conceptual question. So we have a reaction where we have nitrogen reacting with hydrogen to form ammonia. And we have a couple of different pictures of this reaction, right? So we have a before picture, so before the reaction has taken place, when all we have is our 2 reactants, and then we have an after picture. And what they want you to know, or what they want to know, is that if the volume between this before and after picture is kept constant, what has happened to the total pressure during the course of the reaction, right? So the pressure could change, we don't know. The volume has been kept constant, though, as well as the temperature. The temperature has been kept constant, okay? So I want you to look at the before and after picture and tell me what has happened to the pressure over the course of this reaction. So think about it, figure out an answer, and then again, come back to see if you're correct. Okay, so going over this one, remember that pressure is related to a couple different variables, right? So volume, it's related to temperature. It's also related to amount, and this amount is in moles of gas. If the volume is kept constant here between these 2 pictures, and the temperature is also kept constant, then the only thing that can vary is just the number of moles of gas, or the number of moles of, or molecules, the number of molecules in this overall scenario, right? So in the before picture, we've got a bunch of hydrogens. So we've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And we've got 1, 2, 3 nitrogens, right? So we've got, what did I say? 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens, and then 3 nitrogens. And again, this is a mixture, but it doesn't matter because we treat mixtures as just one gas. So we have 11 molecules of gas over here. On the products, though, we have 1, 2, 3, 4. So 4 product ammonias. We also have 1, 2 hydrogen molecules, and then 1 nitrogen molecule. Right, so we have 4, 6, 7. 7 overall versus 11, right? So throughout the course of this reaction, we have decreased the number of molecules of gas. So in doing that, there is a direct proportionality between pressure and amount. If we decrease this one, then we're also going to decrease the pressure. So the pressure here will decrease. B is the correct answer. Okay, so now we're going to start talking about kind of the overlying theory behind the behavior and properties of gases. And so we term this theory kinetic molecular theory, and it's how we try to understand how gases behave, right? So we've kind of already talked about some of the various postulates behind kinetic molecular theory. This is kind of how we got at the idea behind how gases exert pressure, right? But the big idea, or the big hypothesis behind kinetic molecular theory, is that gases are in constant motion. Okay, so that's number one. They are constantly in motion, and depending on the conditions around them is going to depend on how fast they're moving or how much motion they have. Okay, so there are a couple of different postulates that make up kinetic molecular theory. One of the big things that we assume is that the size of the actual gas particles is negligibly small, meaning that essentially we consider these gases to take up no volume. Okay, so with respect to ideal gas, though, that's a big assumption that we make. That is not always the truth. Okay, but for the most part, and for most of the things that we will be looking at, it is a good assumption to make, and we'll move forward with that. Okay, second big postulate of kinetic molecular theory is that the average kinetic energy of the gas is directly proportional to its temperature in Kelvin. Okay, so kinetic energy, the movement or the energy of their motion, is going to be directly proportional to its temperature, and this is in Kelvin. Now, this does not depend on the gas, right? So at a given temperature, with respect to temperature in Kelvin, all gas particles are going to have the same amount of kinetic energy, no matter what gas we're actually looking at, okay? So big idea behind this, that kinetic energy is going to be the same regardless of the actual gas that you're looking at. But just a reminder, what kinetic energy, or how we usually measure it, is that it's 1/2 mv squared, right? Where m is the mass of the gas and v is the velocity, how fast it's moving, okay? So at a given temperature, all gases have the same amount of kinetic energy, and kinetic energy is measured as 1/2 mv squared. Okay, and then finally, the last little postulate of kinetic molecular theory is that the collisions of gas particles are completely elastic, right? So again, we're assuming these guys are moving, they're colliding with their surroundings, with their containers. They're also colliding with one another, right? So when they collide with one another, they are going to exchange kinetic energy. But the big assumption that we make is that that collision is completely conserved, right? So we don't lose any energy. If there's transfer of energy, it's going to be completely transferred to other gas particles, and we're not actually going to lose any energy in these types of collisions. Okay, so now let's talk really quickly about that idea behind kinetic energy and temperature, right? So remember that kinetic energy from a few slides ago, we'll call this kinetic energy average, is related to the mass of the gas as well as the velocity of the gas, so 1/2 mv squared. We also note that at a given temperature, at some sort of given temperature, the kinetic energy of all gases is the same, right? So at a given temperature, kinetic energy of gases is the same. So now, what does that mean with in terms of the velocity of the gases overall. Okay, so let's say that we have some sort of small gas like hydrogen, and we're comparing this to some sort of large gas like argon, right? So argon has a molar mass of about 40 grams per mole, and hydrogen, much smaller, it has a molar mass of about 2 grams per mole, okay? All right, so now, let's say we have a sample of hydrogen, sample of argon. They are both at the same temperature, right? So we'll say that temperature is like 298 or something like that. Because of that, they have the exact same kinetic energy, right? So they're moving with the exact same kinetic energy if they are at the exact same temperature. That does not tell us necessarily about their overall speeds, right? So their overall speeds are not going to be the same. If I have hydrogen, and hydrogen has a very, very, very tiny mass, but it's going to have the exact same kinetic energy as something like argon, which is going to have a much larger mass. And that means for this thing to total the exact same, for hydrogen, this thing, the velocity, has to be much larger, right? So the smaller the mass, the larger the velocity is going to have to be, so that overall we have the exact same kinetic energy comparatively to something that's much larger, which is a much larger mass, that's going to have a much smaller, smaller velocity, okay? Slower, I guess, would be the better way to say that. Okay, so the big idea behind this, and what you should take away, kinetic energy is the same at a given temperature, regardless of the type of gas that you're looking at, though. The velocity is not the same, right? So for the smaller gases, we're going to see them travel the fastest because, again, it's the product of their mass and their velocity that have to equal the same kinetic energy, okay? So the smaller gas, the faster; the larger the gas, the slower. You can take that as just a general trend that you guys should be aware of. Okay, so with that, we can calculate some things. So again, we've just talked about kinetic energy, right? Kinetic energy is 1/2 mv squared. So we can do some weird stuff and just note that this is essentially 1/2 mv squared. We also know that kinetic energy is directly proportional to temperature, and we can substitute the actual proportionality in. When we set these guys equal to one another, we can solve for something called the root mean square velocity, okay? So root mean square velocity, which is what we give this weird little u, so this is u RMS. This is like a special type of average velocity. And again, we made a couple of different assumptions to get to this. I'm not going to necessarily go over those, but just note that this kind of special average velocity is going to be equal to the square root of 3RT over m. So now we should know a little bit about what r is. So r, we have talked already, this capital R is the gas constant. But in this type of situation where we're trying to solve for the root mean square velocity, we're dealing with energies, okay? So anytime we're dealing with energy, and respectively when we're dealing with joules, R takes on a different numerical value. So anytime we're dealing with energy, R is going to have the numerical value 8.314, and the units here are joules per mole Kelvin. So R here is 8.314. Okay, but then you should notice that, again, root mean square velocity, this here, this little capital M, is molar mass. If you look at the trend here, the root mean square velocity, or the average velocity, is essentially inversely proportional to the molar mass, right? So the larger this thing is, now it's really degrading the handwriting. So the larger this thing is, the slower the root mean square velocity, okay? Okay, so a couple other things to note. So again, the root mean square velocity is like a special type of average velocity, right? If you have a collection of molecules, though, and you have an average of their overall velocities, that does not mean that all of the molecules are actually moving at that exact speed, right? Instead, what we see with respect to gases is we get a distribution of speeds that hover around the root mean square velocity, right? So not all molecules are moving at the same speed. Instead, we see a distribution, and then the root mean square velocity is essentially in that distribution, okay? Also, something to note that as we decrease molar mass, like we mentioned before, we're going to decrease, or we're going to increase the root mean square velocity, the average velocity, okay? We will also see kind of a broadening of these distributions as we decrease molar mass. So for heavier molecules, we tend to see a fairly narrow distribution, meaning that all of the molecules in the sample kind of hover about the root mean square velocity, whereas when we get to really tiny molar masses, we see a very broad distribution, meaning that these molecules in these samples are moving at a variety of different speeds, even though we still do have a root mean square velocity, right? So, yeah, that's what I mean by that. Okay. Okay, so we'll also see a variation with respect to this root mean square velocity and temperature, right? So as we decrease the temperature, so as we go from something like 273, now as we increase the temperature, as we go from something like 273 to 2000, what we see overall is an increase in the root mean square velocity. So if you want to imagine the apex of this peak being the root mean square velocity, as we increase the temperature, we see an increase overall in the root mean square velocity, okay? What we'll also see as we increase temperature is, again, a broadening or a spreading out of this distribution. So as we increase temperature, we tend to get a variety of different speeds versus at lower temperatures, molecules tend to hover about that root mean square velocity. Okay. All right, so now let's utilize something like this, or let's actually calculate the root mean square velocity, the average velocity for a molecule. Okay, so the molecule that we're wanting to calculate the root mean square velocity for is oxygen. So we're going to utilize that equation that we derived earlier, where the root mean square velocity is equal to the square root of 3RT over m. So again, m is the molar mass, and they tend to try to use these special little m's that kind of look weird and funky to denote this as molar mass. But just note, for this problem, m is the molar mass, and this is the molar mass of oxygen. Okay, so we should have most of the things that we need. So the molar mass of O2 is just 2 times the atomic mass of oxygen, which is 32, and this is in grams per mole. And then we have R. R is 8.314. And again, it has to be this unit now because we're in joules times mole or per mole times Kelvin. And then T is 25 degrees Celsius. Anytime we use gas stuff, we always have to be in Kelvin. So we're just going to add 273. So we're in 298 Kelvin. So now the only thing I need to mention, one more thing, is the fact that, again, we're using this in terms of joules, right? And joule was our measure of energy. And joule came from kinetic energy, right? So kinetic energy is m, or 1/2 mv squared. The units for a joule, because of that, are kilograms and then meters squared per second squared, okay? Now, if we want all of our units to cancel, knowing that we're dealing with joules here, then the only thing we have to do is we have to convert our molar mass, instead of grams per mole, we have to convert this to kilograms per mole. All right, so this guy has to be converted to kilograms per mole before we can plug it in and get a real answer in our overall equation. Again, because of joules. All right, so to convert from grams per mole to kilograms per mole, all I'm going to do is divide by 1,000, because there are 1,000 grams in every 1 kilogram. And so that gives me a molar mass of 0.032 kilograms per mole. Right? So now everything's ready. We can plug it in. So root mean square velocity for oxygen is equal to 3 times 8.314 joules per mole Kelvin times 298 Kelvin, and this is all going to be divided by the molar mass, which is 0.032, and this is in kilograms per mole. So when we solve here, the units are actually going to end up being meters per second, which is good because that is a unit for velocity. And what we get is 482 meters per second. Cool. All right, so why don't you guys go ahead and try this one. We're looking at xenon, and we want to know what the root mean square velocity for xenon is at 25 degrees Celsius. So think about it, try it out, and then come back for the answer. Okay, so hopefully you gave that a shot, and you got a nice, decent, respectable answer. So only thing that's different here is we're dealing with xenon. So the molar mass of xenon in grams per mole, if we look it up on the periodic table, is 131.3 grams per mole. And again, if we're going to use the root mean square velocity, we need to convert this to kilograms per mole. So I'm just going to move the decimal 3 places to the left, which is what happens when we divide by 1,000. So this is in kilograms per mole. So now URMS, root mean square velocity, is 3 times the same R, 8.314, times T, 298, all over our molar mass of xenon in kilograms per mole, 0.1313. So when we calculate this out, we end up with 238 meters per second. So very fast, but not as fast as oxygen. Again, ideally this should make sense, right? Because the velocity should be inversely proportional to the molar mass, right? So oxygen had a molar mass of 32. Xenon had a molar mass of 131. We had a root mean square velocity of 483 and a root mean square velocity of 283 meters per second, right? So the smaller the molecule, the faster it is. And again, that goes back to the fact that both of these guys have the same kinetic energy, but kinetic energy is mass times velocity squared, right? So if you're not as heavy, you need to move faster to make up for that same kinetic energy. Okay, so we can utilize our little calculation there for root mean square velocity to calculate the speeds of any gases we could possibly want. All right, so now if we consider that, let's consider a little oxygen. Oxygen had a root mean square velocity of 483. I may be making that up, meters per second, but it was in like the 400s. I'm pretty sure about that. All right, so this 483 meters per second is incredibly fast, right? This ends up being something like 1,000 miles per hour, if you want to think of it in terms of what you actually are familiar with, right? So these molecules, these gas molecules, are moving around very, 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 very quickly, okay? So now, let's imagine that you have a bottle of perfume, right? And so you're in a room, fairly large room. Imagine the lecture room, right? And you're in the corner of the lecture room, and you have this bottle of perfume. And you open up the bottle of perfume, right? And so the liquid, or the perfume itself, is liquid, but it's very volatile. So a lot of those molecules are moving into the gas phase, and they're moving throughout the room, right, at these various speeds. So even though these perfume molecules are a little bit heavier than oxygen, they themselves are still going to have incredibly fast speeds as they move throughout the room, okay? Now think about it, right? You're in the corner of the room. How long, if you're in the other corner towards the door, how long do you think it would take you to actually detect the presence of those perfume molecules, right? So it wouldn't be immediate, even though these guys are moving at extremely fast speeds. It would take a while, right? And so that's because these molecules, as they move about, these gas particles, they lack directionality, right? So they will, move from their container, but then they'll collide with the wall and they'll bounce off. And they'll move to another container and they'll hit another molecule and bounce off, right? So these guys are kind of just stumbling about. There's no directionality to them, and so that's why it takes so long for the perfume molecules to get from one side of the room to the other, okay? So from this, we can kind of define something called the mean free path, right? So the more concentrated the molecules are the farther they get before they hit something and collide with it, right? So we can define the mean free path as the distance that molecules are able to move before they actually encounter something and they collide with another molecule, right? So the more concentrated something is, the smaller the mean free path, the smaller distance that they'll be able to travel before they collide with another molecule. That also translates into pressure, right? So the greater the pressure, again, the smaller the mean free path, because greater the pressure, greater concentration, the less distance they're going to be able to move before they collide with something, okay? Okay, so then that process of those perfume molecules spreading throughout the room, that process is called diffusion. And most of you are probably fairly familiar with what diffusion is, right? So in diffusion, we see things moving from a high concentration, which is what you're going to find in your perfume bottle, to low concentrations. That is the spontaneous natural process with respect to diffusion. There is also a special type of diffusion called effusion, right? So effusion is the process by which a gas molecule is going to escape a tiny little hole into a vacuum, okay? So both effusion and diffusion depend on the overall velocity of the particles, right? So the faster something is moving, the faster the rate of effusion, right? Also, the faster the rate of effusion, right? So the larger the velocity, the faster these things diffuse, the faster they effuse. And again, velocity has to do with the overall size of the particle, or the molar mass of the particle, right? So the smaller the particle, the faster it's going to go. That also means the greater the rate of diffusion, the greater the rate of effusion, okay? So we only kind of invoke this idea of effusion at this point in time because there is a special law that deals with it, right? And the special law that deals with effusion, which again is the movement of gas particles through a tiny hole into a vacuum, this special law is called Graham's law of effusion. And so what it tells us is that the rate of effusion of one gas over the rate of effusion of a different gas is equal to the square root of the molar mass of gas B divided by the molar mass of gas A, okay? So how do we use this? Why do we even bring this up at this point in time? I don't know anymore, but with respect to Graham's law of effusion, I know this is a means by which people can determine the molar mass of something, right? So let's say you have some sort of unknown gas, you want to determine the molar mass. You can compare it to a known gas and its molar mass and its rate of effusion, and using Graham's law of effusion, you can calculate the unknown molar mass, okay? So I don't ask this, not on exam, but I think I did include a question, unfortunately, on the homework set, because I don't know why. I don't know why I did that, but I did, so I apologize. Okay, so let's actually show you how to utilize it, so maybe you could answer that if you possibly wanted to on the homework problem. Okay, so we have a unknown gas, right? And we have found by using effusion, this technique of effusion, that it effuses at a rate that is 0.462 times that of nitrogen gas. We're going to calculate the molar mass of this unknown using this overall data, okay? So Graham's law of effusion is going to allow us to do that. So first thing we're going to do is we're going to say we have a rate, and we're going to say this rate is of nitrogen gas, right? So we have rate of nitrogen gas. We don't know what that rate is, but we're just going to leave it like this. And then we also have another rate. We have the rate of the unknown, and we know that this is 0.462 times the rate of nitrogen gas, okay? So that's number one. Now, we're going to set up our little Graham's law of effusion. So this says that the rate of, let's say we'll call nitrogen A, and then we'll call our unknown B. The rate of A, the rate of nitrogen, over the rate of the unknown, that's not how you spell rate either. The rate of unknown is equal to the square root of the molar mass of the unknown over the molar mass of nitrogen, okay? All right, so now we also know something about this rate of the unknown. So we're going to take this, the fact that it's 0.462 times the rate of nitrogen, and we're going to substitute that in. We're also going to substitute in the fact that we do know the molar mass of nitrogen. So this is just 2 times the atomic mass of nitrogen, which is 28 grams per mole. Okay? All right, so now, rate of nitrogen over 0.462 rate of nitrogen, that's the rate of the unknown, is equal to the square root of molar mass of unknown over 28. Okay, so we substitute everything in we know. Now we'll find that these rate of unknowns, or rate of nitrogens, pardon me, will cancel, and we're going to be left with 1 over 0.462 is equal to the square root of, let's say this is x over 28. Okay, so 1 divided by 0.462 gives us 2.16 equal x over 28. To get rid of the radical, or get rid of the, is that what that's called? To get rid of the square root, we're just going to square both sides. Square both sides. So we'll square this. That leaves us 4.69 is equal to x over 28. To solve for x, we'll just multiply both sides by 28. And that gives us x, or the molar mass of this unknown, equal to 131.2. And that's in grams per mole. Right? So that's great, right? What is this unknown? Well, if we look at the periodic table, and if we remember the previous problem, xenon had a molar mass of 131.2 grams per mole. What had happened there, right? So this could most likely be xenon, right? So we've identified the unknown using Graham's law of effusion. That is great. Okay, so last little thing, right? So when we deal with gases, we deal with them as being ideal, right? But gases are not ideal always. Sometimes they behave like real gases, which deviate from ideality. So 2 of the big assumptions that we make when we assume that a gas is ideal is that we assume that there are no attractions between gas molecules, and that gas molecules themselves do not take up any space, right? So they essentially account for none of the volume that they're in. That was one of the big assumptions of kinetic molecular theory. All right, so where do we actually start to see these assumptions that we have made break down? So 2 different cases at low temperatures, right? So at low temperatures, we'll start to see deviations from ideality, also at very high pressures. Okay, so at high pressure, at low temp, we'll see deviation, and we'll start to see these guys behave as real gases. Okay, so why does this affect anything? Well, at high pressure, we're going to start to essentially increase the concentration overall of the gas particles. So at really high pressure, they're going to get really, really, really close to one another, and so that assumption about volume and them taking up no volume breaks down, because at some point in time at high enough pressure, they will begin to account for a large volume of the container. Okay. Also, at low temperatures, their speeds slow down quite substantially, right? And so because their speeds slow down quite substantially, what we will start to see at that point in time is that if there is any type of intermolecular attraction between the molecules, they will start to be attracted, and they will start to spend more time with each other than with colliding with the walls, which is what creates our overall pressure, right? So if they spend more time with each other, because they're actually really attracted to each other at low temperatures, then they don't collide with the walls as much, and so they start to stop exerting the pressure that they should if they were ideal, okay? All right, so that is it. I don't care about real gases, and I don't want you to calculate anything with respect to real gases. Just note that we do start breaking away from ideality when we have low temperatures and very high pressures.